The theme of lecture, the magnetic field. We have four questions. And the first question is the force exerted by a magnetic field, motion of a point charge in a magnetic field, torque on current loops and magnets, and the whole effect. The whole effect. And the first question, and we know the first characteristics of magnetic field, magnetic induction, and magnetic field. Some points the space can be demonstrated in the compass with the compass needle. If where the magnetic field, the needle will itself in the direction of the field. Experimental is observed with the charge. Charge of charge Q has a velocity in magnetic field, and the force is a proportional electrical charge and field and velocity, and sine and of angle between and mu and magnetic induction. These experimental results can be summarized as follows. When a charge moves with the velocity and magnetic field, the magnetic force and a moving charge will be an electrical charge multiplied by velocity and magnetic field. If the perpendicular force is perpendicular to both velocity and magnetic induction, is perpendicular to the plane defined as two vectors, is the direction of force is given by right hand rule, as the velocity is rotated into magnetic field. And here this is illustrated right hand rule for determining and the direction of force exert on the charge moving and magnetic field. The force is perpendicular. To both and velocity direction and magnetic induction direction, and the direction advance of the right hand turn in the same direction. Rotate and rotate and V into B. And there was if the fingers of the right hand are and the direction of velocity, this is, and here, and such they can be circled into B, the thumb points in direction of the force in here. The force in here. Yeah, examples of the direction of the force exerted on a moving charge maybe in here. This is the direction of the velocity, and when the magnetic field vector B in vertical direction is given in the three figure, and vertical direction in here. Not the direction of any particular magnetic field can be found experimentally by measuring force in here. This is direction, and here this is direction, and velocity for several velocities there for different direction. This is direction on here, but in here perpendicular and the force, and here direction the velocity may be in here this direction of velocity by we use and three axes, y axis, z axis, and x axis. In here, in future direction of the magnetic force of the charge particle with moving velocity in a magnetic field B. When a wire carries a current in the magnetic field, this is photo figure. Wire segment of length. This is length of the wire carrying current. In here, this is direction of the current. If a wire in the magnetic field, there will be force on each charge carries resulting in a force on the wire, and the number of charge in the wire segment if in the number n per unit volume times the volume AL, this is area, this is segment, and L, this is length of the wire, is the total force on the wire segment is here. This is force, total force in here. This the formula. And then the force can be written in the magnetic force as a segment of current carrying wire in here. And where is L and the vector whose magnitude. Magnitude is the length of the wire and whose direction is parallel to the current. Parallel to the current. For the current is a positive because x direction, and the magnetic field is a XY plane in here. This is XY plane. Is the force on the wire is directed along the positive z axis. The direction of the this is the direction of the force on the wire directed along the positive z-axis and shown as a figure in here. This is formula magnetic force on the segment of carrying wire in here. And we now the two important difference between electrical field lines and magnetic field lines. We know, and electrical field can be represented by electrical field lines. Magnetic field can be represented magnetic field lines. But compare two electrical field lines, two characteristic electrical field and magnetic field. Electrical field lines in the direction of the electric poles on positive charge, but the magnetic field lines are the perpendicular to magnetic force on moving charge. Electrical field lines begin on positive charge and on negative charge. Magnetic field lines form closed loop. Since isolated magnetic poles apparently don't exist, there are points in the space where magnetic field lines begin or end. And here this the like little compass and needles iron fillings line are up tangent to magnetic field lines in here, to magnetic field lines. And B, and here this is drawing config lines for the situation shown in situation and figure A. In here this is closed, and in here this is closed, and here this is direction of magnetic field in here, there. Okay, and the second equation, motion of a point charge in a magnetic field. We know the magnetic force on the charged particle moving through a magnetic field, always perpendicular to the velocity of the particle, but in here, and this is a charged particle movements and plane perpendicular to a uniform magnetic field. In here, the orbit of charged particle in uniform magnetic field. And here, this is direction of the charge moving on the right angles to uniform B. And this is direction of the uniform magnetic field lines. And this is in the circle with a constant speed, because and v and velocity are always perpendicular to each other, and the constant v constant. And here this is a radius of the circle, and there are three positions, and one position, second and third, and this is direction of velocity, and this is tangent line, one the direction and force and velocity perpendicular each other. And here this is a direction of the with direction and centripetal force we know, and using formula of the Newton's second law, we know formula Newton's second law of F equal ma, and this is direction of centripetal force, this is direction of centripetal acceleration. We know, and acceleration, centripetal acceleration, we replace formula v squared divided by r, and this is direction of the Lorentz force, and angle between force and velocity equal 90 degree, and Lorentz force equal Newton's second law. Newton's second law. In here we to find radius of the orbit, mv divided by qb. M as this is mass of the particle, v acceleration, and b magnetic field and q electrical charge. We to find the period because charge electrical charge move on the circle. The period is related to the speed. We know formula 2πr. R this is radius, and radius replace mv divided by qb, and final formula of the we obtain the period of the particle circular motion. And cyclotron period, they called the cyclotron period 2πm divided by qb. We calculated frequency, cyclotron frequency. We know formula of frequency inversely proportional and period, and final formula qb divided by 2πm. And the third form, the situation, torque and current loops and magnets. A current carrying loop experiences not a force in uniform magnetic field, but it does experience a torque that tends to twist it. This is N, and here this is figure, and here this is N. Orientation of the loop can be demonstrated, described by unit vector N, perpendicular to the plane. In here this is plane, and vector unit vector N, and perpendicular to the plane of the loop, and illustrated in the figure. The orientation of current loop and perpendicular to the plane, and here this is B, and right hand rule for determining the sense of n vector. N vector when the fingers of the right hand swirl around the loop in the direction of the current, the points in the direction of n. And in here it's true. The figure shows the force exerted uniform magnetic field or a rectangular loop, whose the normal unit vector n in here, normal unit, and n vector angle, and n makes an angle theta with the magnetic field B. And here this is theta angle between n vector and magnetic field. The net force on the loop is 0, and the two force or the force magnitude equal each other, and electrical current A, and one side on the rectangle, E, and multiplied by magnetic induction. The annex, and the torque can be rewritten in the term of the magnetic dipole moment mu, also and magnetic moment of current loop, which is defined as the magnetic dipole moment of current loop, and n multiplied by electrical current, area, and vector n. And system international unit of magnetic ampere multiplied by square meter in the thermomagnetic dipole moment. The torque on the current loop is given by magnetic moment multiplied by magnetic induction, and B. And the final equation, the Hall effect. We reality is on the force acting on the moving charge. We know in the conductor in a magnetic field and demonstrated Hall effect. The effect analogous to transfer deflection of electron beam in a magnetic field in vacuum. The effect and discovered in American physicist Hall in 1879, while he was still a graduate student, to describe this effect and consider and conduct on the form strip as shown in figure in here. The force in here. Force and on charge carries in a conductor and a magnetic field. In here, this is negative charge carrier electrons. In here, the charge the charge carriers are pushed toward the top of the strip in here, and as a point A, and the point A is at a higher potential than point B in here. A point and a B point in here. And this is negative charge, positive charge carries the total, the charge carries a gain in here. We know, and here this is direction of electrical field, and plus from plus to minus. In here this is positive charge in here. This is negatively charge. Is the charge carries again, push it towards the top of strip, and this is direction of electrical field, and we know and moved and the electrical charge, positively electrical charge. In here, this is direction of the force, and direction of the velocity, because the charge carries again pushed toward the top of the strip. So the polarity of potential difference is opposite to that for negative charge carriers. And there in here the potential difference between top in here, and this is top and bottom of the strip, is a whole voltage. We can calculate it, and the magnitude of whole voltage is the term drift velocity. We know, and the magnitude of magnetic force, we know this is a formula and following, and Lorentz force is this magnitude. Magnetic force is balances electrostatic potential of magnitude. We know, and electrostatic force and magnitude electrical charge multiplied by electrical field, where is the and E is the electrical field due to charge separation. E we know, and the electrical field, and we have an electrical field velocity multiplied by magnetic field. E we and here this is the whole voltage is a 4. Therefore, if the with the strip and W, the potential difference is the whole voltage is a 4 in here voltage, or whole voltage and electrical field multiplied by and with those 3 is the omega, and maybe and B multiplied by multiplied by velocity, drift velocity is E, and final formula, the current density in here, the current density and QVD, eliminating and drift velocity between this equation, and Q and Q in here, this is and Q equal, and current density divided by drift velocity and therefore drift velocity and voltage. Voltage E, and replacing here in final formula, in here final formula, and Q equal minus J current density and negatively current density multiplied by magnetic field and the electrical field, the whole effect. And here we studied and magnetic field characteristics, the first characteristic, magnetic induction, and we illustrated the direction of the force and direction of the magnetic field lines, and compare with the magnetic field lines, compare with the electric field lines, and compare each other, and we studied a whole effect. Thank you for attention.